Hey folks, I'm going to do a few special cases of uses of second law, and I'm going to focus on situations where there are two objects, and those two objects are connected by a rope. We will study Newton's third law later in the course, but we'll start to see some ideas from it here or later in the unit. And so this first example is a cart, a mass, and a pulley, and the rope connects the cart to the mass, and the rope is draped over the pulley. And so one of the first things I want to tell you about rope is that the rope determines the axis, and the axis actually changes direction whenever the rope changes direction. So we didn't get to see this in class at any point yet, but this cart would be on a track. The tracks are pretty close to frictionless as far as we're concerned. Pulleys are pretty close to frictionless also. And then this mass is just kind of free floating in the air. And if you're holding the system, obviously nothing happens. But if you like let go of the cart, the mass begins to fall and the cart begins to move toward the pulley. And because this mass is in some version of free fall, they accelerate. And so, I could ask you like different questions about this, but the question I'm going to focus on is deriving an expression for the acceleration of this system. And whenever you have two objects or more in a system, there's two options. There's analyzing individual objects within the system, and then there's the system approach. And I think you'll see eventually that the system approach is a lot easier to do some things, and then in certain situations you can't use the system approach only. So we'll start with an analysis of single objects. And so I'm going to do two free body diagrams. I've labeled them capital M and lowercase m because I want you to understand that in this situation, typically the mass that's hanging has a smaller mass than the mass of the cart. So we'll start with a free body diagram for big M, which is the cart. So cart goes here. And as far as the cart is concerned, there are three forces acting on the cart. There's the weight of the cart. Now, something that hopefully I mentioned in class already, but I might not have, is the equation for the force of gravity on an object is its mass times little g. So instead of writing Fg here, I'm going to write capital M, lowercase g. So the force of gravity on the cart is its mass times 9.81. And you'll see me start to do that in a lot of free body diagrams. There's another force that's acting upwards, and that is the normal force. And then the third and final force acting on the cart is the force of tension. Now, the cart is going to accelerate to the right, and so the tension force is the force that causes it to do that. And I'm going to label one more thing on the cart. I'm going to draw an arrow that's kind of floating off to the side, and we're going to say that that direction is the positive x direction, which makes sense because the cart is moving horizontally to the right, and so we'll make that the positive x direction. Short story, you get to choose which way this points when you start to set up your problem. So we're going to leave that there and say, well, the tension force is going to be a positive force. Okay, so next up, we're going to look at the hanging mass. And for the mass, the free body diagram looks simple, but it's like critically different. So the mass has a force of gravity on itself, and that's going to be lowercase m, lowercase g. So the force of gravity is mass times little g, and this has a smaller mass. The upward force is the tension, and there's a couple things about this. These two tension forces are the same value. So those those arrows should be congruent, but there's only one rope connecting them, and so those two tensions have to be the same, because a rope can only produce one tension in our like slightly simplified existence here in AP Physics 1. The critical difference about this free body diagram is that in our picture, the rope changed direction. And so what was the positive x-axis up here continues to be the positive x-axis even after the rope passes the pulley. And so on this diagram, the positive x-axis is down. And so if you have any situation where there's a rope that's strung over a pulley, and therefore it changes direction, just know that that axis moves with the rope's direction. That doesn't happen if we have if you're like hanging a painting and there's a rope hanging, rope behind the frame, where the rope kind of does this around some central hanging point. Those tensions don't have to be equal. They usually are, but they don't need to be. It kind of depends on how you've set up the hanger. Anyway, side story. So here's the individual approach. And so what I'm going to do is I'm going to write net force expressions for both the cart and the mass, and then we're going to combine them. So for the cart, I kind of recognize by now that the cart is not accelerating in the vertical direction. So if I don't need the vertical net force, I'm not going to use it. So I'm just going to say net force in the x direction equals mass times acceleration in the x direction. And for the cart, it's pretty simple. The net force in the x direction is the tension force. The mass of the cart is capital M, and it has some acceleration. This acceleration is directed along the positive x-axis. So that's kind of it. For the cart, I'm going to do this. Oh, I'll do it over here. For the cart, it's the same idea. And it's the same acceleration. Because those objects are connected by a rope, they have the same properties at all times in terms of their kinematics, and so they'll have the same acceleration. Now for the net force on the hanging mass, I have to be a little careful because this is the positive x-axis. The positive force in this situation is mg, and the negative force is tension. And this is equal to mass times acceleration. Same acceleration, different masses, because they are different objects that have different masses. And so I have these two expressions. And so we're going to imagine that the question is, what is the acceleration of this system? And so I have to solve either equation for acceleration. And the only bad news is I can't do that because the tension is unknown. And so when you have multiple objects and you're searching for a single variable, you will often run into this situation where you have two equations that you've written and two unknowns. And so you have like a couple things you can do. You can substitute, which will work wonderfully in this equation, or you can add equations together. So I'm going to just tell you, like you can say, okay, well, tension equals big M times AX. So I can put big M times AX in here and solve, and I'll be good. But I'm going to do something a little different that maybe you've not seen before, and I'm going to add these equations. And I'm going to take Ft equals capital M times acceleration, and I'm going to take mg minus Ft equals little m times acceleration, and I will add those equations. Immediately, the tension term is gone because it's tension minus tension. And what I'm left with is mg equals, I'm adding these two terms, so I can say acceleration times big M plus little m. And so I have now eliminated the tension, and my final expression for acceleration is mg over the sum of the masses of the two objects. So this would be one answer to the question. Okay, so that's one approach, and that is very thorough. And if your question is not what is the acceleration of the cart, then this is actually the way you want to go, because chances are good you'll be answering a different type of question that requires these equations up here. Maybe like, what's the tension? But I wanted to show you one more thing, and that is the system approach. And this one's a little weird at first. If I'm drawing a free body diagram, I am now going to draw the entire object, the entire system, as if it were one object. In other words, pretend that these objects, big M and little m, are the same object, and then draw a single free body diagram for them. So this is a little strange. Because of the way you circle this, you want to notice that there's no contact with the rope. Technically speaking, there's no contact with the table, but if I just cheat a little bit and say, oh, there it is, there's a table. There's a table touching big M, and so there has to be a force from that table. And so we get these forces, but they're going to look kind of bizarre. So I'm going to label all of the external forces. The normal force is hopefully still obvious because the table is not part of the system. There's that support force on big M. There's a downward force, and that is big M times G. So the weight of the cart is an external force because gravity comes from the earth, it comes from outside my system. And so here's where things get kind of weird. Tension is no longer the external force. You can think of it as it's pulling on this cart and it's also pulling on this cart. That's actually why it canceled in this equation. The only other external force is the weight on this block right here. But we're going to do things kind of differently because this string changed the direction. This weight is actually, as we saw here, directed in the positive x direction. So the way it's going to appear on this free body diagram is little mg is actually going to be pointing to the right because that is the direction of the rope and the positive x-axis. And so something happens very quickly that makes things really easy. And in fact, I'm going to show you something else. Because I'm fake asking you the question, what is the acceleration of this object? The way that that's written, it's going to be the net force over the mass. So I can actually write this expression immediately. The net force is the sum of all the forces on this object. Normal and gravity for big M balance, but mg is not balanced. So the net force on this object is mg. That's the net force, and so it's the only unbalanced force there. There's nothing to like add or subtract from it because there's no other horizontal forces. And then the only thing you need to do to be careful is the mass of the system. The mass of the system is the combined mass of the two objects. And so I wanted to show you this because for finding acceleration, it is very easy. In terms of what to do on an exam, the AP Physics 1 exam might ask you to derive something, in which case it's going to kind of force you through the individual object approach. But if it doesn't, then you can just kind of think about this full system free body diagram and write the net force expression with the total system in there. So I'm going to stop this video. I'm going to record an extra video if you want to use it of a couple other examples that I will go through more quickly that have to do with multiple objects, but that's the general idea, that the rope determines the direction of the positive x-axis, and then you can either draw free body diagrams for single objects or for the system on the whole. Thanks.